Great. Okay, thanks everyone for joining, and we're really pleased to welcome Frank Dudbridge, who's Professor of Statistical Genetics in Leicester and has an honorary professorship. Stand back. Stand back. And everyone will see you. I can hear you. Anyway, I think you could hear me. So Frank, you have to stand quite a way back, otherwise. Yeah. Anyway. And Frank's going to talk to us about objective measures of statistical evidence, and I'll get away as fast as I can. Right. Thank you. I think it's quite tempting to talk to the remote people and ignore the room, so I'm going to ignore this camera and just stand here. There you go. Yeah, well, thanks for having me. It's great to be back. Yeah, it's been a while, and I think, like the rest of us, I've probably spent a bit too much time on my own over the last couple of years, and this, I'm going to show you the results of this, and hopefully something relevant is going to come out of it. So here's a brief outline. I'm going to talk a bit about. I'm afraid there won't be any genetics in this. This is really about doing statistics and how we report evidence from statistics. And so I'll quickly go over these ideas and a couple of areas in which I think we can improve the way that we report our statistical analyses. All right, so you might have seen this paper, and there have been a few others like this. There's a lot of discussion now in general about improving research practice, but also in statistical reform, and statistical significance has been a whipping boy, I guess, for a lot of this, and an easy target in some way. So, we do a lot of hypothesis testing in research work. The classical methods which we all use, but we also kind of aware at the same time that they're plagued by logical fallacies and irrelevance to researchers' goals. So we control type 1 errors, but we're not actually interested in type 1 errors. It's other kinds of errors that we are trying to control, and we're kind of aware of all this, but we carry on anyway, and things seem to work quite well. But they occasionally do lead to problems and controversies when results get discovered that maybe shouldn't be reported. So the Bayesian approach is the alternative, but they are difficult. They're mathematical, they're complicated, and then there's more subjectivity involved. So you and I will never get the same result. So these are the standard ways of doing things, but there's this increasing recognition that something has to change. And so there's been a steady stream of position statements coming from different communities. This is the American Statistical Association put out a statement on p-values. A couple of years later, this special issue of the American Statistician, full of, I think, 20 different papers with different suggestions on how to move beyond traditional testing. And then in response, we had a task force which now came back and kind of redefended the traditional approach based on p-values. So even the American Statistical Association can't quite make up their mind about what we should be doing. And at the same time, we get these various papers to either redefine or retire or even abandon statistical significance. So a lot of discussion around this. So just to let you know where I'm coming from, here are a few of what I see as the salient points. So our classical tests, our standard tests we do all the time, they do work most of the time, and that's why we're all here, and why we've got publications and jobs. We mustn't forget that this does a pretty good job for us most of the time. So any replacement must work at least as well. The debate is really around p-values and how they can be misinterpreted or over-interpreted. So you kind of read too much into your results, p-hacking and so forth. And underlying all of this are kind of more fundamental issues. What is the error rate we're really interested in controlling? So the type 1 error is, given that the null hypothesis is true, what's the probability of our result? But maybe the null hypothesis is never actually true. So is that really a relevant error rate? Is it really false discovery rates? And even if we've decided what is the error rate, how do we actually choose what level to set it at? Why is it p of 5% or 5 times 10 to the minus 8? How do you choose that without going to the Bayesian world? Quite difficult to do. So you might be a Bayesian, and we can claim that we're now asking the question we really want to answer, i.e., is that hypothesis more probable or more likely than the other one? The problem is that there's no right answer for a particular case. Right, and there are various flavors of so-called objective Bayes, different attempts by people to come up with standard prior distributions that you could use in Bayesian analyses, so that you have a baseline result. But there's more than one approach to doing that. You get effects like the so-called Jeffreys-Lindley paradox, which I'll give an illustration of a bit later on. So this is not a panacea either. You can take a step back and say, well, do we actually want to be making an inference at all? Do we want to go from data and actually say, here is an effect, we have discovered something? You know, who's auditing the null hypothesis? Is there somebody out there counting all the occasions where the null is true and saying, well, actually 5% of the time somebody reported a false positive, and they're also counting all the times when the null was true and nothing was discovered? Yeah, that's not really happening. Arguably, sometimes people write papers, you know, there was this, what do they call it, the psychological reproducibility project. So every now and then somebody surveys a whole field and they count how many, you know, how many true and false positives may be published. But in general, it's a bit unclear who's interested in, you know, in the false positive rate. If you're Bayesian, you can get some kind of probability or degree of belief about your test, but what does that really mean in practice? You know, what if you have 81% and I have 79%? What does that really mean? Yeah, what's the difference? So there are interpretations in terms of betting behavior and losses and gains under decision theory, but that's not really what's happening in the real world, right? We're not actually laying bets. We're not actually getting financial benefits from the outcomes of our tests. You get this probability, but it doesn't really have much relevance to what we're actually doing in the real life. So my point here is that you know, these are the standard paradigms, but they all assume some kind of process of inference that we are not actually carrying out in the real world. Okay, this business of type 1 errors and degrees of belief, these are purely rhetorical devices that we use to help us make an inference, but we're not actually literally interested in what these paradigms are doing. Certainly in exploratory research settings. So we have these evidential points of view coming instead. So instead of actually making an inference, we'll simply measure how much evidence is in the data, and we separate the measurement of the evidence from any actions that we will take or inferences or beliefs that arise from the evidence. And we'll focus our attention on the evidence in itself, and we'll say, all right, here's the evidence, and we can measure that objectively. And then we can do different things with that evidence later on, but that's a separate enterprise. Okay, and you know, in many situations, what really matters is building up of an evidence base. Okay, and as the evidence base gets large enough, then it becomes a bit irrelevant how we actually make an inference. We come to a community conclusion based on an evidence base. So you can think, especially in healthcare, you know, something like smoking, we all believe smoking's bad for us causally. That wasn't based on a single study with a p-value, that was based on many lines of evidence. And over time, that became overwhelming to the extent that it doesn't really matter what your prior probability was or what your type 1 error rate is. It's simply an overwhelming evidence base. Vaccines may be a good example. So, you know, some of us, myself included, were a little bit worried about the COVID vaccines when they first came in. After a week or two, it became clear that they were quite safe, and you know, and now most of us are happily taking vaccines. We believe they work, and that's based on accumulation of evidence. Or something like homeopathy, where maybe the evidence is in the other direction. You know, some people believe in homeopathy and others don't. And again, the evidence base is there, but maybe less extensive, and there's a certain degree of prior belief combined with that. Okay. So the idea, again, is maybe not to worry about significant results and discovery rates, but simply to quantify evidence, and as that evidence base gets large enough, then the inference becomes a communal effort. Right. So this, I think, plays into this larger discussion, and this is why I wanted to come and talk to you about it, really, about the reproducibility crisis and these efforts in reforming research culture. Okay. So, you know, I don't really need to tell you here because these are a lot of your papers, but the emphasis increasingly is on reproducible research. It's not enough to have one massive convincing study. You have to have several complementary studies, perhaps using different designs, which are all pointing towards the same conclusion. And it's that overall weight of evidence from different directions that leads to a consensual inference in the end. Okay, it's worth pointing out that a lot of these things were considered in the GWAS world before the rest of the world sort of caught up, and we were quite early to recognize that a single significant GWAS result wasn't enough. You had to always hold back some of your data for an independent replication. And I think this is now percolating into the research world, the wider research world. Yeah, it's not enough just to repeat experiments. You need different kinds of experiments, reproducible studies. Okay, so there's a paper from Marcus here, and I'm really kind of interested in this part of the cycle here. Okay, analyzing data and interpreting the results. And how are we going to interpret our statistical results in a way that encourages reproducibility? So you may say that we do this already when we do significance testing. So we do this all the time. We measure an effect size, a beta, an odds ratio, we give it a confidence interval, and we report a p-value, and we say, this shows evidence of an association, blah, blah, blah. And we have different values of p that have some colloquial meaning, nominal, genome-wide significance, so forth. Okay, and these work quite well in an informal way. It's worth pointing out there's no real rationale for these terms. So, even I propose this threshold for genome-wide significance, but that's based on correcting for multiple testing to get you back to 5%, and there's no real rationale for 5%. Okay, and what we call suggestive or borderline, again, is simply some device for helping you get a paper published. Okay, but what you can say about p is that it does put your test into a rank ordering. Smaller p sort of goes with stronger evidence for an effect. Yeah, so we like to say if p is small, then our data are unlikely under the null hypothesis. And you can kind of wave your arm and say that means probably the other alternative is more true. Even that's a bit dodgy, because under the null, all p-values are equally likely. So small p-values are unlikely, but large p-values are equally unlikely under the null because they're uniformly distributed. So if I say a small p is strong evidence, I'm making some implicit statement that the alternative hypothesis is more likely to give you a small p-value. Okay, so you can argue that we do this already, but the one thing that the statisticians have agreed on is that p is not a great measure of evidence. You can read this for yourself maybe, but there are lists of qualities that a good measure of evidence should have, and p doesn't really meet those criteria very well. Okay, I think one particularly noteworthy thing is that a large p-value does not imply evidence in favor of the null. Yeah. So if p is large, we say, well, we don't reject the null, but we don't actually accept it either. We just remain undecided about things. And what you would like is a measure of evidence that can increase your confidence in either conclusion. So a better approach is to go with likelihood ratios. And there's kind of philosophical writing behind this. So the so-called law of likelihood, which says that the data are evidence supporting one hypothesis over the other if the likelihood ratio kind of is in the direction of that hypothesis. So if the data are more probable under hypothesis one, then the data are evidence in favor of hypothesis one. And we can measure the strength of the evidence with a likelihood ratio. And this is what happens in forensic statistics, right? So if you ever go to court and you hear DNA evidence in court, then they present the evidence as a likelihood ratio, and they don't draw a conclusion from that. They basically say, here's the likelihood ratio, and that's a bit of evidence, and you must now consider that along with all the other hearsay or circumstantial evidence pertinent to the case. Okay, and then the verdict, they call them the fact finders, they come to a verdict based on all the different lines of evidence beyond a reasonable doubt. Okay, so they've kind of agonized over this for a long time in the forensic world, and they've come to this conclusion, at least in the UK. And a kind of accessible application of that, and I can kind of give a mention to my colleagues in Leicester here. This isn't the criminal case, but this is the identification of Richard III. So, lots of different analyses of different type of data, and in the end, they get a likelihood ratio of 6.7 million. Okay, now you don't form a conclusion from that, but you can say that that's strong enough to overcome any reasonable doubt you might have about being Richard III. Okay, so this is what they do in forensics, and the argument is that we ought to be taking a similar approach in other applications as well. Measuring evidence and then sticking it out there along with different lines of evidence. Okay. So the question is more generally then, what counts as strong evidence? So I can give you a likelihood ratio and say, right, here's a number, but what are you supposed to do with that? If you're not going to have some threshold of significance, then how can I say whether this is strong evidence or not? Okay, so a number of authors have proposed scales or descriptive scales for likelihood ratios. Okay, and what you can see here is that different authors have got different levels that they consider to be substantial or strong. Not only that, but the adjectives they use are different as well. You might also note that some of them have got the same thresholds, but they have different adjectives. So for Jeffreys, 10 is substantial. Goodman calls that moderate. A lot of heterogeneity in there. Also worth noting that these are all men who lived in the 20th century, and as time goes on, and people who don't speak English start doing more statistics, then these kind of subjective terms start to become a bit more vague, and they might start meaning different things to different people. So for me, this isn't really good enough if you want to be doing this in a systematic way. Is there a more rational way of describing evidence, in ways that we can use in discussing the import of our research? Okay, well, we can use Bayes' theorem as a model here. So this is called the odds version of Bayes' theorem. So it tells us we have prior odds. This is the prior belief, if you like, in two hypotheses. So how much do you believe in the null compared to the alternative? You multiply that by the likelihood ratio to get posterior odds. It tells us how your beliefs are modified in the light of the evidence. Okay, so we use the likelihood ratio as the measure of evidence. Now, although I've shown Bayes' theorem here, I'm not going to use it literally. We're using it as a kind of model for learning. But we're going to focus on the likelihood ratio, but we accept that ultimately it's going to be used in a learning process. And the model that we'll use for that is Bayes' theorem. Right, but I'm not going to take it literally to do my inference. You'll see why I take this position in a minute. Okay, so if we're working under Bayes' theorem, we can say, first of all, let's assume that any conclusions that will eventually be drawn, they will depend on the probability and not the odds. Okay, so I showed odds on the last slide, but they contain the probabilities, and it's the probabilities that will drive the decisions. So we can relate the likelihood ratio to the probability on the log odds scale. So if we take the log of the prior odds and then we add it, we add the log likelihood ratio to get the log of the posterior odds. Okay. Then I say that we can model this with a logistic function mathematically, and the slope of that function is what I call the effect of evidence on probability. Okay, now you can think of this like logistic regression. Okay, so when you do a logistic regression, this here is your outcome. This is your log p over 1 minus p, which you might have done. And we're used to having a beta coefficient in a logistic regression, and we call that the effect of the exposure. Yeah. So this is exactly the same as a logistic regression model here, except that my outcome is the probability of the hypothesis, and my exposure is the evidence. Okay, so the effect of the evidence is the slope of the logistic function. So this is the logistic function here. This is how I rate the log odds to the probability. And if I add something to the log odds, and that's the likelihood ratio, the log likelihood ratio. So if I add something to the log odds, then I've also increased the probability. Yeah, and that increase is the slope of this curve here. Right, so in the blue line, this is the slope of the black line. Okay, so the slope of that curve is the effect of evidence on probability, and we can understand that to be belief. Okay, so the effect of evidence on belief. So we can see that the effect is strongest here, right? So the slope is strongest here, steepest slope. This is where the log odds are 0 or the probability is 1/2. So that means you kind of have equal belief in the two hypotheses. Equipoise, we call that. So that's where the effect of evidence is greatest, is when you have a neutral belief between the two hypotheses. And the effect of evidence is minimal here, and that's where the probability is maximal, is at 1. And also down here, we have minimal effect of evidence. Okay, so we can say that the effect of evidence is greatest at equipoise, and the effect of evidence is least at certainty. Right? And it's kind of intuitive, right? If your beliefs are completely set in stone, then no amount of evidence is going to change your mind. Or if you're completely equivocal about things, then that's how your mind can be changed most easily. So let's make this a definition now. By definition, we'll say belief is weaker when evidence has a stronger effect on your belief. Okay, and stronger beliefs are defined to be those beliefs where evidence has a weaker effect. Okay. And if you can all kind of go away and think about examples, from real life where this seems to make sense. The stronger you believe something is another way of saying you're less likely to change your mind, even if you're given evidence. So now let's define what we mean by weaker belief and stronger belief. Okay, so there's no hard threshold between them, but we can say if we want to make a distinction between weaker and stronger belief, then where is that distinction sharpest? Where can we make the sharpest distinction between weaker and stronger belief? And because we've defined those in terms of the effect of evidence, where is the sharpest distinction between weaker effects and stronger effects of evidence? Okay, so this is the effect of evidence here. Where is this changing most rapidly? Right, and this is where I can start to do your head. And so I'm going to look at the slope of this curve now. Where is the slope of this curve maximal? You have to do some calculus here, and luckily somebody in Poland has done this already. And to cut a long story short, the sharpest distinction occurs here with the probability just under 80%. Right, so here, this is where the slope of the blue line is maximal. In other words, the slope of this line is changing most rapidly. This is going from a steep slope and it's flattening out, and this is where it's flattening out at the highest rate. Okay, so the log odds are here and the equivalent probability is up there. In other words, it's just under 80%. And I think that matches a bit with intuition. Yeah. So when you talk about, oh, I'm 80% sure, yeah, that corresponds to a stronger level of belief under this definition. So it's not a hard threshold, but note that I say weaker and stronger, and not weak and strong, but if I want to say where things become stronger and where they become weaker, then I'm saying about 80% belief is there. So we can now define weaker beliefs and stronger beliefs by this range here, and similarly weaker disbelief. So probability is below 1/2. That's this range of the graph here. Okay, so these are definitions. Weaker and stronger belief. Now moving to evidence then. If I want to measure the evidence, let's define a unit of evidence as the amount you'll need to change weaker beliefs to stronger beliefs. Okay. So more technically, it's the minimum evidence that would update any weaker belief to a stronger belief. So in other words, any weaker belief in this range is going to get moved to a stronger belief in this range by 1 unit of evidence. Okay, so that corresponds then to basically the width of this interval here, which is a likelihood ratio of 3.73. And from the same definition, well, if I just go back again, we could say if I've got weaker disbelief, so I start here, any probability in that range will get updated to this range by 1 unit of evidence. Okay, so weaker disbelief, so weaker disbelief will get updated to weaker belief by 1 unit. And from the same definition, 2 units will get you from weaker disbelief to stronger belief. All right, so I'm mildly skeptical. I get 2 units of evidence, and now I'm kind of fairly confident. That's the kind of way we can describe it. So we can plot or tabulate the prior beliefs to the posterior beliefs that way. Now that I've defined 2 units, I can say, well, what if I had weaker belief to start with, and then I got 2 units of evidence? That's moving me to a stronger level of posterior belief. So let's call that much stronger belief. Okay, so I've defined a new category here, and that corresponds actually to 93.3%. So, and again, informally, we like to talk about being 95% sure about something. So there's a rough definition of much stronger belief. Now, having defined that category, how much evidence would get me from here, from weaker disbelief to this new category? That's 3 units. And it's a likelihood of a ratio of 52. And you can carry on forever. So you can define more and more categories of belief, much, much stronger, much, 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 much stronger. All right, and gives you a way of, if you observe any likelihood ratio, you can convert it to a unit of evidence, and it gives you a qualitative interpretation of any likelihood ratio in terms of how much belief you would have relative to your prior level of confidence or skepticism. So I'm kind of speaking to this urge to give some interpretation to these numerical measures we get. Yeah, we can get a likelihood ratio, and what are we supposed to say about it? And it turns out that people want to talk about weak and strong evidence. So we have some way now of objectively converting it from a quantitative scale to a more qualitative scale. So on the right, you'll see, my proposal, and this is how it stacks up against previous ones. And you can see they're all kind of more or less in the same ballpark, which is reassuring. I mean, these guys are pretty bright, yeah, pretty smart guys. And I claim to have found a kind of a rational way to compromise, between these different proposals. It's kind of interesting, if you look at wagon makers on next to mine, they have a very similar kind of scaling, but everything's just a little bit lower as well. And they set out consciously to compromise between the previous proposals. Yeah. But again, their compromise was still subjective in its own way. And what we have is something, I think, that's a little bit more objective here. Yeah. All right, so that's kind of my proposal for describing strength of evidence. There's still one big problem for people like us to actually put this into practice, and that is how do you deal with a composite or a vague hypothesis? So what we do most of the time is have a point null, log odds ratio of 0, and then we want to compare it to a general alternative hypothesis. And we can't get a normal likelihood ratio for that because we don't know what is the likelihood for a non-zero beta, because we don't know what that value of beta is. And to do that, you have to work instead with Bayes factors instead of likelihood ratios. Now, I've got the same version of Bayes' theorem here. It's exactly the same as before, but this is now called a Bayes factor. And the Bayes factor is an average of likelihoods where you've taken an average over a prior distribution for your odds ratio, for your log odds ratio, or your beta coefficient. You need some kind of prior distribution, and then you can average the likelihood ratios over that prior distribution. And what we want is for this prior to be objective. We want an objective measurement of evidence. And that's kind of where things start to get complicated. So here's an example. So we toss a coin 100 times, we get 60 heads. The question is that a fair coin or a biased coin? Okay, so classical test gets you a P of just over 0.05, so almost significant, but not quite. Now the Bayesian analysis, so here are 3 so-called objective priors that you could use. So I mentioned that there were different flavors of objective Bayes, and so in fact 4 if you include the BIC, okay? So it turns out that under these 3 different priors, you have pretty much the same posterior probability of a bias. That's saying if I estimate the probability of throwing a head, Okay, what's my belief that that's greater than a half? So the probability that we have a biased coin, it's about the same over these three priors, but they give quite different Bayes factors for a bias. Okay, so that's our first problem, is that depending on the prior that we've used, we get quite a variation in the Bayes factor. And our other problem is that these Bayes factors are all in favor of a fair coin. These are all less than 1, which means that these are saying we have evidence for a fair coin when the probability, there's the distribution of the probability of heads. So the estimation side of things is telling us that we have a biased coin. Right? So we're used to taking estimates of parameters and p-values, right? And they tend to agree. In this case, in the Bayesian test, the estimate is not in agreement with the Bayes factor. And this is essentially because we've used vague priors. Okay, these make no assumption about the probability of heads. And so the Jeffreys-Lindley paradox has a more precise statement, as you can imagine, but intuitively, this is the problem, is that if your prior is too vague, then you'll end up with no evidence for that hypothesis. And if you're comparing it to a sharp point null hypothesis, then you will always end up favoring that point null hypothesis. So if your prior is too vague, you'll end up with a measure of evidence that is at odds with the parameter estimate. So what can we do about this? If we're going to use a Bayes factor, what distribution can we use in it while remaining compatible with the parameter estimate? And yet at the same time, we want to be objective, we want to be vague with respect to prior knowledge. Can we actually do this? And for me, the only way you can do this is actually to take a posterior distribution under a vague prior. All right, so if we're not sure what a posterior distribution is, what I mean is take the point estimate and its standard error, okay, and that defines a kind of distribution on the parameter. All right, so this gives rise to what we call posterior Bayes factors. So you estimate the parameter from your data, and then you take that estimate back in and calculate the Bayes factor using that estimate. And that gives you what is called a posterior Bayes factor. So this was proposed about 30 years ago, and it didn't go down too well with people, and so it sort of died a rather quick death. Here's kind of what some of the strongest arguments is. The procedure has little Bayesian justification. If you're Bayesian, you have to have a prior, and then you modify it, and then you get a posterior. It doesn't make sense to have a posterior and then take that back in and use it again as the prior in the same data. That violates the Bayesian philosophy somehow. It doesn't have frequentist optimality properties. It's not derived as a frequentist procedure. Therefore, frequentists are so-called supposed to be unhappy as well. And he yields counterintuitive results, which can actually be debated. Okay, so their position was Bayesians won't like it and frequentists won't like it, so we should kind of throw it away. But life is full of compromises, right? And you can also take the view that if you want a compromise approach, then you have to do something that compromises both positions. And so I came to this by thinking that this is the only way we can get a Bayes factor that is compatible with the estimate. Yeah, so it's really the only way we can do it. And I've said earlier that in the real world, we're not doing proper Bayesian updating, and we're not doing frequentist testing either. What we're really doing is, what we want to do is get an objective measure of evidence, which we can then just take into our kind of real world growth of an evidence base from which we will draw conclusions as a community, as time goes on. So what we really want is a nice interpretable and objective measure of evidence. And it's great if it's got Bayesian justification, and it's great if it has frequentist optimality, but that's not my main priority at this point. Yeah, what we want is a nice measure of evidence that we can interpret. So that's why I've gone back to this idea. There's still this issue, though, that we seem to be using the data twice when we do this. Okay, we use it once to get this posterior distribution, and then we use it again to get a posterior Bayes factor. And we all know that using the data twice is supposed to be naughty. We overfitted the data or whatever. But the question nobody has actually seemed to ask is, okay, if it's using the data twice, to what extent is that actually giving us a bias? To what extent does it overstate the evidence? So the way I thought about this was like this. So supposing I get my posterior distribution from my data, and then I go out and get a new independent data set, and then I use this as the prior distribution in my new data set. Nobody would have a problem with me doing that. Now, I'm not actually going to get a new data set, but I could calculate the Bayes factor I might expect in new data while using this posterior distribution as the prior in new data. Okay, and if I calculate that expected Bayes factor, that gives me a sense of how biased is my posterior Bayes factor, compared to a proper Bayes factor I would get in future data. And rather beautifully, if you work it out, the expected bias, in a certain sense, is half the number of parameters. And the proof is very similar to the proof of AIC. Okay, so when you do AIC, the bias is the number, it's actually the actual number of parameters under this framework. And then you multiply it by 2 because, well, just because. Okay, but in this scenario, the bias is half the number of parameters. Okay, so we can correct the posterior Bayes factor for this bias, and we have what I'm now calling the empirical Bayes factor. So it's a bias-corrected posterior Bayes factor. And my claim is that this can be interpreted on the same scale and in the same way as an ordinary Bayes factor, or indeed a likelihood ratio. All right, so some equations, and this is just to show you that you can calculate these quite easily. This is what we do most of our time. Yeah, we have a parameter and we divide it by a standard error, and we think we have a normally distributed variable. So we have a z, plug it into that formula. There's your expected or empirical Bayes factor. You can do one-sided, one-tailed test as well, and you can do chi-squared tests, in one line of code. So going back to our 60 heads and 100 tosses, we see that the empirical Bayes factor is 3.17. So it's greater than 1. So it's in the direction of a biased coin. And that's now concordant with the parameter estimate. And that's exactly because we have used the posterior distribution in the Bayes factor. Now, going back to the units of evidence I was talking about just now. Okay, so we have this definition of 1 unit of evidence that updates weaker belief to stronger belief. That's a Bayes factor of 3.73. We can give nice rules of thumb here. Now, if we take these to be empirical Bayes factors and we refer back to the equations on the last slide, we can work out what p-value does that correspond to. And lo and behold, I have proved for the first time that p less than 0.5 represents a modest level of evidence. Yeah. I mean, it's fantastic. It's fantastic stuff, actually. I tried to be modest, but I fell off my chair when I saw this. It's really rather beautiful. And any p-value of less than 0.2 is a Bayes factor greater than 1, so it's an evidence in favour of an effect. Okay. And in fact, yeah, if you go further down the table again, these are the kind of p-values that we're used to. And we're used to dividing them by 2 and going down by a power of 10. So it all lines up really, really rather nicely. So now you might be saying, if you have an equivalence between p-values and empirical Bayes factor, you can plot one against the other, and on the log scale, it's pretty much a linear relationship. Right? So this is a p of 0.1 here, and any p-value less than that, you can more or less read off a linear relationship with the EBF here. So you might say, why do we need this at all? Yeah. So we can now give an evidential interpretation to a p-value, and this is my answer really. So some of us grew up measuring temperature in Fahrenheit, and then somewhere along the line, everybody changed to Celsius, and they both measured the same thing. There's a linear relationship between the two. So why move from Fahrenheit to Celsius at all? And the answer is it's all about interpretation. Yeah, there's a more kind of intuitive or logical interpretation for the Celsius scale than there is for the Fahrenheit scale. And as my claim here, again, if you want to work with the p-value, you can, but you could work with the z-score as well if you want. But for me, you can convert this to an EBF, and this gives you a much more interpretable scale. Yeah, interpretable scale of evidence. And this is where I am at the moment. I still can report p-values and read p-values in papers. So whenever I see a p-value, then I say, okay, well, that corresponds to, if you see one here, then that corresponds to 1 or 2 units of evidence. And I know what that means in terms of how it should modify my skepticism in the result. So here's an example that maybe helps to show it's kind of a subtle but important shift in how we interpret results. So this was some controversy about some experiments designed to detect ESP. And in one of the experiments, we have a P of 0.002, which we are used to calling evidence against the null. But somehow we're obliged now to reject the null with that small p-value. If you're working in psychology and that's the kind of field-wise accepted level of significance of 0.05, let's say, then somehow, you're obliged to reject the null whenever you see that. Because if you don't reject the null, then, who says when you reject it and when you don't? You'd have to throw away a lot of valid results as well. So you get this kind of dual nature between using P as a measure of evidence, but also using it as a justification for claiming an effect. And then when you claim this effect, you then get letters to journals and a lot of controversy. So the subtle but important change is to separate the evidence from the conclusion. Okay, so we have the same result here, which corresponds to 2.7 units of evidence. That is still evidence against the null, but we're not making any claim necessarily about whether there is ESP or not. And in particular, if I had prior skepticism about ESP, that's not going to change my mind about it. What you can do is say with 2.7 units, maybe that's justification for trying to replicate the study and to grow the evidence base. Right? And so indeed, people did go out and try and replicate it. And they didn't, as you might imagine, they were unable to produce further evidence for ESP. Okay, so I think, it's maybe a bit subtle, but I think it's an important distinction you can make between a classical interpretation of a test and this evidential interpretation, where we can simply say, well, look, we found this much evidence and there it is, and this is what we make of it, but you're allowed to make something different of it. And in turn, I think, if people move towards this mode of thinking, then it's one small step towards this wider enterprise of reforming research culture. Okay, so that's the story basically. So we want to be reporting evidence in data and focusing on that evidence as part of a broader program of inference, not necessarily drawing the inference from our own data. In order to do that, and in order to have a discussion section in our papers, then we can have these units of evidence that convert a quantitative measure to a more qualitative scale that allows discourse. And in order to deal with composite hypotheses, we have these empirical Bayes factors, which are objective, interpretable, and indeed compatible with what we are working with already. Okay, so that's where we are. So there's more to come with this. So there's a version for multiple testing, which is pretty much online now as well. I think this also fits in nicely with the idea of triangulation as well. So evidence from multiple sources, and then we want to make some reasonable conclusion based on those. And that doesn't fit immediately into Bayesian updating, but this idea of maybe there's a calculus of credibility that we can draw, and it may be that where we can use this kind of Bayesian updating idea to and objective measure of evidence might be a nice way to move forward a bit in triangulation ideas. So yeah, hopefully I've enthused you in some of these ideas, and be very happy to discuss further. Thank you very much.
Well, I don't know. I was just going to say that was great. That was genuinely one of the most interesting seminars I've heard for a long time. I'm sure there will be a lot of interest here. You know, it's always said that Fisher, you know, semi-intuited things, and then after the fact, either got the maths right or sometimes wrong, and then was corrected, but eventually reached, you know, got the answer, and that fiducial, the whole disaster of fiducial inference was that he finally couldn't actually get an answer for that, so it was a big smoke screen about why he had made it without admitting he was wrong. So maybe you'd have saved him, but getting neither Bayesian nor frequentist answer for 0.05. But I'll questions? Jim.
That's so interesting. I'm sort of just trying to make sure that I understand. You know, I don't understand it. But I wondered if, like, I suspect it has no impact, but like the shape of the link function that you use to go from a sort of quantitative degree of evidence to a qualitative assessment probably has some impact, like use the logic, but I guess you could use other shapes.
You could, yeah. So I use the logic because of Bayes' theorem. Yeah. So the odds version of Bayes' theorem we showed here, that induces that logistic relationship. But yeah, so in version 1 of the paper, I also did it for a probit model. So I was arguing that if you're interested in tail probabilities, you could follow the same logic with a probit model, and we actually got P of 0.05 through that as well. But that went down badly with reviewers, and I kind of rejected that line there.
So what was the problem with that? Why is that?
That was more closely tied to a prior probability of 1/2, and it was less interpretable with other prior probabilities, basically. Yeah. It's a bit hard to really kind of give you more detail on that, but yeah, it was too closely tied up with one particular value of the prior.
If anyone's got any questions online, they could put them in the Q&A. Have you tried it with sort of updated meta-analysis? Is that a sort of situation?
Yeah, that's something to be tried, I think. Yeah.
Could that be
yeah.
Lots of comparator approaches.
Definitely.
Next, so thanks for, I mean, I agree with Jim, that was just totally fascinating, and then lovely circularity about it at the end. But I mean, it works, it just, the very logical, the way that you deliver is the units of evidence and their ability to convert a slightly more subjective feeling about appraising or making, drawing inference from evidence is great, but assumes that those units of evidence are all the same. And I guess I guess this might relate to George's point, but in any one experiment, that's fine. But converting that to the real world, where evidence from any one test may be more or less relevant for trying to interpret an overall reality.
Yeah.
Does this offer any help in trying to bring together problems of triangulation over and above the existing regime where you just grab the estimates and hope for the best? I don't know.
So I think that's what I meant by calculative credibility at the end. So you might have several Bayes factors from different kinds of study, and you might want to weight them according to how credible you think that evidence is. And this might be an easier way of doing that than, you know, currently, I don't know, you might do a weighted meta-analysis or something like that. So.
Because if it was possible to generate weighted units of evidence from different sources, that would be exciting too.
I think so. Yeah, but I think it needs a bit of philosophy behind it. I think you can't just kind of say, well, here's Bayes' theorem and let's just stick another weight into it. And I think it needs a little bit more behind it.
I think you've knocked them all dead. So, Caroline.
Hi, Frank. Well, my head's still spinning. So thank you a lot for the talk. Super interesting. I was just wondering, when you talk about updating your prior beliefs, would it be the idea that this would be a subjective individual decision, or is it the idea that the body of evidence is used to keep updating your beliefs?
Yeah. So the way I see it is that everybody's got their personal belief, and we all see the same evidence, right? We all read the same journals and read the same papers, but we might all have a slightly different personal belief. But at some point, it all converges when there's enough of an evidence base. Yeah, we all start to believe that cholesterol is bad for your heart, let's say. So that's why it matters less about taking Bayes' theorem too literally. Yeah. With enough evidence, it doesn't matter so much. Of course, we might disagree about when that level is reached, but that's kind of what happens in the real world, isn't it?
Jim?
I was just going to ask, so sort of when you compared the scales to other methods that have tried to come up with something similar, what has been the reasons that those haven't been widely adopted in the past?
I think the lack of power is the main reason. So I think not so much the scales of evidence, but the objective priors that have been used. And BIC we all know about, for example, they tend to conflict with a p-value result. So you have a significant p-value, but the Bayes factor is nothing. So I think that's mainly why it hasn't caught on. When people do use the Bayes factors, they've tended to use the Jeffreys scaling, and that's simply because Jeffreys is very clever and very famous, right? And kind of developed the whole field. But is that really a good enough reason to standardize a scale? And you were saying I'd have probably fallen out with both Fisher and Jeffreys if I didn't come up with this in the 50s. So I'm quite glad that I'm alive now.
So Fisher wrote a paper people don't quote by Fisher about card turning. You see, in a journal of psychic research, because he had a very strong belief in ultimate indeterminism, which allowed him to remain a very orthodox Anglican and a sort of semi-materialist. And he thought that sort of God existed in this sort of things, allowed things just to flip slightly the wrong way, and that was how God worked. And so he was invested in showing that people could make judges on people could telepathy worked and things like that. So he'd like that. I mean, it wouldn't have the it's like the homeopathy example. Yeah.
People seem to find what they want in Fisher's writings. I mean, he's quite often quoted, saying that one result is not enough, and what you need to do is have a result that you can replicate many times. So it's a reproducibility people grab that as well. Yeah.
And his thing about, and it's not 5, as you said, it was doing offhand, sort of say, another day he might have said something else.
Yeah.
It's just the truth. So thanks. You're around all today, aren't you? You do.
Yeah, I'm around till about 3:30.
Oh, okay.
Yeah.
But what time is the interview? Mock interview?
1 o'clock, I think.
Okay. So after 2.
Yeah.
You're around for a bit after 2. So Marie will know where. He's been here.
OS 15 apparently.
OS 15.
Okay. Yeah, if you want to drop in and chat after the event.
Brilliant. So thanks again. I'll pop down after the interview.
Okay.
After the interview. I was really interested.
Oh, great.